Lionel Messi kicks a ball towards a target at the base of the goal. The ball travels at 7.0 meters per second at a 30-degree angle from the ground. If he succeeds in hitting his target, how far away was it from when he kicked the ball? Okay, so clearly this is a question with a projectile, which is a ball, and this is clearly a projectile motion problem. And all projectile motions problems have two dimensions. They move either up or down, or side to side, left to right. It could be north, east, south, west, or up, down, left, right, whichever. But it's important especially when you're using numbers, to determine which direction is positive, because we'll be using a lot of vectors in these kind of problems. So for this case, let's just make anything moving upwards positive, down negative, anything moving to the right positive, and to the left negative. So now let's try and draw this problem out. Let's make a field right here. This is your ground. It's going to be a target right over here. Nice big red target. And then there's also going to be a Lionel Messi, who's standing right over here. It's my best attempt at someone kicking something. A very focused Messi. And the ball's right over here. He's kicking it. He's going to kick it. And the ball travels all the way over. And hypothetically, it hits the target. Hooray. So the information that's given is that this ball, when it initially is kicked, travels at 7 meters per second. And this line right here, this tangent, is at an angle to the ground, and that angle is 30 degrees. So given these two pieces of information, this and this, we can create a triangle to model the scenario. So that would be, here's the ball, that's 7 meters per second going in that direction, and then here's a 30-degree angle, here's the ground, and here is your right angle. Now this is a diagonal line, and it's traveling in that direction at that velocity on that diagonal. But really, to solve a two-dimensional problem, we need a Vx. Let me do a different color. Let's do magenta-ish. So you need a Vx, and then you need a Vy. And this really just makes it into two one-dimensional scenarios, and that makes it a lot easier to work with. So now, given this triangle here, we can solve for Vx and Vy using our trig ratios. So let's just solve for Vy first. Okay, so Vy. And using the sine ratio on this 30-degree angle, since it's opposite, and the hypotenuse is right over here, Vy is equal to 7.0, wait, let's keep the colors consistent. It's equal to 7.0 times the sine of 30 degrees. This value makes Vy equal to 3.5 meters per second. Similarly, if you were to draw something up for the x, the Vx, we can say that it is the cosine, as this side is adjacent to this 30-degree angle. It's right next to it. Vx, we can say that it is 7.0. It is 7.0 cosine 30 degrees. So Vx is, when you put this into your calculator, you get 6.1 meters per second. So now let's just write down what we know about our x and y. Let's move over a bit. Let's write down what we know about our x and y. So our x let's keep the same color. So our x, we know that your velocity is going to be 6.1 meters per second. Velocity in the x is 6.1 meters per second. But that's just about all we know about it. We don't know its displacement in the x. We don't know the displacement. That's what we need to find. And we don't know the time. However, in the y, we know the velocity, which is right over here. So Vy equals, I should say V1y, and I'll get to that in a minute. It'll be 3.5 meters per second. Now, this velocity, I put the 1 there because there is an acceleration component in the y direction. Let's go back to the diagram for me to explain this really quickly. When moving this ball, when it's moving in this arc, it has both an x component and a y component, which is constantly changing in comparison to this x component. And this is because of gravity. And gravity has a constant acceleration of, in this case, negative 9.8 meters per second squared. This is a negative value because, remember, we set downwards, which gravity acts to, we set downwards as negative. So what else do we know about this problem? So v1y8, and then we know the displacement in the y direction as well. It's going to be 0 meters because really the height of the ball hasn't changed from where it started, which is right over here, to where it ended. The ball's height in relation to the ground has not changed. It has been the same. And we do not know delta t. One important note that we need to make is that since it's the same ball, this delta t right over here and this delta t right over here, they are the same. And for that reason, since we cannot solve immediately for velocity in the x direction, or sorry, the displacement in the x direction, we can use this delta t once we solve for it here, plug it into this formula right here, and we can solve for our answer. So let's solve for delta t. So we need the kinematic equation of delta dy equals to v1y, your initial velocity, times delta t, plus 1 over 2a delta t squared. Now we know that delta dy is 0, so we can cancel that out. That's gone. Now delta dy is 0. Now v1y, now we can see that it's a quadratic because there's a t squared over here, something in the second degree. So let's just rearrange it to 1 over 2a delta t squared plus v1y delta t. There's something more familiar. Now let's plug in these values, whatever is there, into here. So we have 0 equals to 1 over 2 negative 9.8, that's gravity, delta t squared, plus 3.5 delta t. This we can simplify to 0 equals to negative 4.9 delta t squared plus 3.5 delta t. Now, there lies a common factor between this term and this term, and that would be delta t. So we can factor it out and we can get 0 equals to, what will we get? Delta t. Whoops. Stuck with that color. Let's go 0 equals to delta t. That's 1. And then you have negative 4.9 delta t, because it had 2 of them. There were 2 of them. We took out 1. plus 3.5. Now from here, we really just factored out the entire quadratic, so we can say that this delta t right over here is, when we set it to equal 0, is just 0. Now this one, on the other hand, is going to be, is going to be the more useful one. It will be 0 equals to negative 4.9 delta t plus 3.5. And now this is just a linear system. We can just solve for delta t. So bring 3.5 to the other side, becomes negative. Negative 4.9 delta t, we get delta t equals to negative 3.5 over negative 4.9, which yields 0.71 seconds. Now going back to this list of data that we collected, or information that we really created, we have delta t here now, which is 0.71 seconds. And since it's the same, we can plug it back in here. We get 0.71 again. Now we can solve for delta dx, which is what this entire question is about. Take all this data, and we get the base of the equation, which is velocity in the x direction, equals to displacement of the x in the x direction divided by time. Now we know velocity, and we isolate for delta dx. That would be vx delta t equals to delta dx. Now delta dx equals to 0.71 is time, and then we have 6.1 as our velocity, and delta dx equals to 4.3 meters. 4.3 meters. And there you have it. The ball in this scenario travels 4.3 meters in total from here to here. Hope this video is informational and helps out.